and has been active in fusion research for 45 years. Beginning in 1984, he developed a detailed quantitative theory of the functioning of dense plasma focus device, or DPF. Based on this theory, he proposed that the DPF could achieve high ion and electron energies at high densities suitable for hydrogen-boron fusion and space propulsion. First with funding from NASA's Jet Propulsion Laboratory, and then with investor funding for LPPFusion, he and a small team achieved record-high temperatures, 100 times that of the center of the sun. He is also a leader in developing an alternative to the Big Bang Theory and is the author of the 1991 book, The Big Bang Never Happened. In both fusion and cosmology, his work has been published in leading peer-reviewed journals. Please we welcome Eric Lerner.
And thanks for organizing this and inviting me. So today I'm going to be talking about focus fusion as the fast path to fusion energy. We believe the fastest path. So I don't need to tell you, the headlines tell you, that humanity is in crisis. What the headlines don't say is this crisis has been building for quite some time. These graphs illustrate this over the period since the Second World War. So the blue line shows the rate of mortality decline. So since the rate of decline is a good thing, the higher this number, the better, the faster people were getting their lives better. And you see that there's a peak there right about in the 1960s. So indeed, the 60s were the good old days. This is the fastest rate of mortality decline. And then you see the blue curve declines during the 70s and 80s into the end of the 20th century. There's a small blip, which is mainly associated with the integration of China into the world economy. And then with the pandemic, we actually move into negative territory so that the mortality rate of the entire world population is now rising. As a condition for progress in the post-war boom, we needed energy. So the orange curve is the rate of energy increase, percent per year. And again, it closely tracks the blue curve. For humanity to advance, we need more energy flow. So again, the peak is during the 60s. There's a decline to a low plateau, almost stagnation, through the end of the 20th century, a small peak during the period of the integration of the Chinese economy, and again a transition during the present decade into a decline in per capita energy increase. So what do we need to reverse the situation? First of all, we're not sustaining ourselves on a global level. So this is a map of the net reproduction, the number of children per couple, for countries in the world. And basically, only the warm-colored countries, which are overwhelmingly Africa, have positive levels necessary to sustain the population. All these other countries are having less than 2 children per couple, which obviously is unsustainable for the survival of humanity. And the countries that have more are the very poorest countries where the mortality rate is the highest. So how can we change this? We can't resolve this crisis with fossil fuels. We can't drill, baby, drill. Present-day fossil fuels putting aside any effects on the climate, creates 7 million dead per year. This is directly through the health effects of fossil fuel air pollution. Every decade, the same number of dead as the total deaths from World War II. The cost of fossil fuels are crippling the world economy. $5 trillion a year in direct costs equal to half of global manufacturing output. This is like taking the manufacturing output of the United States, China, and Japan and sinking it into the ocean. The true cost of fossil fuels has been estimated by many sources as approximately $10 trillion a year. We need higher energy density. Every time humanity has advanced in its technology, it has been by making energy denser, getting more energy out of less mass. Right now, we are consuming 14 billion tons of fossil fuels, 2 tons per capita. To advance, we need a denser energy source. This is a comparison of the amount of mass needed to produce a given amount of energy. At the beginning of the modern period, we transitioned from a wood-based economy to coal, then oil, and gas. So you notice a doubling and then a tripling of energy density. That is the key change that allowed the development of modern technology. We'll be talking about these little squares here. This is the amount of fusion fuel, 5 kilograms, that's needed to produce the same amount of energy as these thousands of tons of fossil or wood fuel. Solar and wind, which have been discussed as alternatives, are also very dilute energy sources. For wind and solar both, you need about 1,000 tons of material to produce a megawatt of continuous power. 1 billion tons per year would be needed for 1 terawatt. And to produce that amount of new energy would need about $5 trillion per year. So again, solar and wind as base load, not intermittent sources, are extremely dilute and extremely expensive sources. So what is the alternative? The only alternative, actually, as a much denser source of energy, is fusion energy. Now, fusion energy is the power that drives the universe. It's the basic source of energy for stars like our sun. It's the densest form of energy known, and it is possible to achieve this energy source by 2030. Now, that sounds crazy because, of course, people who know anything about fusion energy know the joke that it's the energy of the future and it always will be, or it's always 50 years away. Well, this is based on what I call the old approach to fusion, which also is not energy dense. If you look at the dominant international fusion projects, they're the National Ignition Facility, which at the moment holds the record for fusion energy production, and the giant tokamak, which is under construction in the south of France, and it's called, in French, ITER, because it eats everybody's budget. You can see for scale the human beings in the laser that supplies the National Ignition Facility. You probably can't see the little guy here, so we put him in a circle that describes the scale of the ITER tokamak if it ever is built. Last year I was at a conference at the ITER site. I could not get far enough from the site to fit it in its entirety within the view of my cell phone, and I could only compare it in scale as a cross between a Star Wars Death Star set, except it's real, and the pyramids. This is an enormous enterprise, and by coincidence, if functional, it too would use resources at a rate of about 1,000 tons per megawatt. What is a new approach? Well, the approach that we have is called focus fusion and does produce the highest energy density that we can obtain. It's under development, but if it works, we will have 5 megawatt generators this size, which is about 0.6 tons per megawatt, so more than 1,000-fold increase. A focus fusion is our name for a combination of the device, which is the dense plasma focus, and hydrogen boron fuel. So let me describe what I mean by this. Hydrogen boron fuel is the ideal fusion fuel because hydrogen boron combine at high energy to produce alpha particles. Let's see whether we can. Nope. There we are. Come on, baby.
Is it a video?
Yeah, it is a video. Blast. No, we didn't have time to test this.
Is your video embedded or?
Can we just,
She's asking, is it embedded?
Is the video?
yeah, listen, can we just quickly shift to the PC? No, it will just take a second. No, this can plug in directly. And we need to,
On this side.
okay, and we need to connect this.
So we're gonna have to do this.
And then here.
On this side. And I'm struggling to get either. There we go. And missing. Yeah, connect. Yes.
How do we explore?
Scott, where's the monastery?
At the bottom, the explorer at the
That's a
bottom.
screensaver. I didn't take the picture.
Where is the,
Ceramic building.
there?
Yeah. There you go.
Come on. And then we have,
The Big Bang mile. Is it Big Bang mile?
Oh, it's a
gotta be
USB.
An external device, so we need to scroll down. Yes, okay, USB drive.
Ah, okay. That's it.
Fusion media.
Great.
All right. We should be back on track. Okay. So the proton and the boron get together. They can't stay together because they're too excited, and they break up into 3 helium nuclei and no neutrons. So the important thing is the energy is in the form of moving charged particles. So the energy is instantly released in the form of electricity, because electricity is by definition moving charged particles, and no neutrons. That's extremely important, because with no neutrons, you can have high energy density. With neutrons, you can't, because neutrons are not only dangerous to humans, they're very destructive of material structures. So if you have a fusion fuel like deuterium plus tritium that produces all of its energy in the form of high energy neutrons, they're breaking apart the structure of steel, of whatever you're made out of, your machine is made out of. So you have to make the machine very large to spread out the neutrons. So you immediately get low energy density. With hydrogen boron fuel, you have almost no neutrons, none from the main reaction, and from secondary reactions, you're down by a factor of 1,000. So that means you can shrink the device and make it extremely energy dense. Second of all, you can, now the fuel is abundant. There's no radioactive materials involved. Boron-11 is 80% of natural boron, and they can be separated because there's a 10% difference in their mass by chemical means. Hydrogen, of course, is abundant in water in the oceans, so you have no problem with resource shortages. There's no radioactive waste. Everything contains radioactivity. All of us are radioactive. But radioactive waste is defined as long-term radioactive substances at levels that are dangerous to humans. We've done calculations, and by carefully selecting the materials that the device is made out of, we will get 0 radioactive waste. Direct conversion to electricity. We're going to go into this a little later in the lecture, but the main thing is because you have moving charged particles, you can get the electricity into a circuit directly without going through producing steam, running a turbine and a generator, which is what we've been doing since Edison's time. And that is all extremely expensive. And finally, you can get decentralized power. That's extremely important for the stability of the grid. The grid has been destabilized by many things, including deregulation. One of the things that makes the grid unstable is the necessity of sending power from centralized generators over long distances to the loads. This way, decentralized loads will be fed by decentralized generators. Now, hydrogen boron is something that the idea has been around for decades. We're not the only private fusion company that's working on this. There are bigger companies, TAE out on the West Coast, HP11 in Australia, Marvel Fusion in Germany, that are also working on this fuel. But the other thing we're doing that's unique is the device, which is called a dense plasma focus. So the dense plasma focus device is itself extremely small. The heart of the device is the electrodes, and I'll show you how they work. But you can see one of my colleagues' hands to give you the scale of the electrodes. This is not like either. This is a device whose heart you can hold in your hands, and the entire device fits in a room that's 13 by 13, not the pyramids. This is the beryllium electrodes installed. This outer ring is the cathode, the inner is the anode, and there's an insulator in between. Why is it stuck? Oh, never mind. Our approach is very different from what most of our colleagues. Plasmas are inherently unstable. One of the main reasons they're unstable is because of the pinch effect. When currents are moving through the plasma, they create magnetic fields that attract the currents to each other if they're moving in the same direction. So that creates filamentation. That's a big instability. Most of our colleagues try to get rid of those instabilities. They try to make the plasma sit still, like a good dog. Well, that's pretty much impossible. At least it's extremely difficult. In nature, we see plasma at all scales in the universe, and plasma is 99.99% of the universe. And we can imitate those processes of filament creation and use them to concentrate the energy in the plasma rather than fighting them. So we sort of call this the Wright brothers approach, because if you recall from your history, the Wright brothers were able to beat a giant government project to create heavier than air flight by studying how birds control their flight. So they were imitating nature, and that's what we too are doing. And this Veil Nebula is an excellent example of the filamentation process. And you can see the almost fractal structure of filaments within filaments. So this is how it works. Let's see. So we have several stages of concentration of energy. The first stage is a capacitor bank releases electricity to the electrodes, which are in a small vacuum chamber about this size that is filled with the working gas, either deuterium or hydrogen boron. This forms filaments of current, and the filaments of current are pushed by electromagnetic forces down the length of the anode. This is all happening in approximately 2 microseconds. So even though the amount of energy stored is very little, our device stores 60 kilojoules. 60 kilojoules, I like to say, is about the amount of energy you derive by eating 5 pistachio nuts. So it's a very small amount of energy. But because it's concentrated first in time by being released in only a few microseconds, and in space within the small volume of the electrodes, the amount of power generated when our device is on is approximately equal to that of the northeastern United States, hundreds of gigawatts, but only for a few microseconds. So that's the first instability that we exploit. Now, when we get to the end of the electrodes, everything funnels together into a hole in the anode. And the approximately 64 filaments that are formed merge through the pinch effect into a single powerful filament carrying the full 1.8 megaamps of current. So now we have a third instability, which is the kink instability. So the kink instability starts to pull the current into a twisted wire. And I see plenty of people here who remember what that wire reminds them of is a landline telephone. Maybe not all of you have seen such a thing. So the landline telephone continues to twist itself up through a second order pinch to form a plasmoid. So a plasmoid is a self-contained, magnetically self-contained, three-dimensional object which is contained by the powerful magnetic fields produced by the currents. So no external magnets are used in this device. Because it's a pinch device, the magnetic fields are supplied by nature. And nature can supply a lot more magnetic field than we can artificially, because instead of thousands of Gauss or tens of Tesla, these magnetic fields get up to millions or even billions of Gauss. So the plasmoid shrinks down and in the process heats up. What's basically going on is a form of frictional heating. It's viscous heating that converts the powerful kinetic energy that the plasma has acquired from the magnetic fields into random or thermal energy. So that heats it up to the point where we can have the collisions of the boron and hydrogen ions. And we have actually achieved, and we have published in peer-reviewed journals, that we have gotten up to as much as 260 keV, which is the equivalent of approximately 3 billion degrees Kelvin, which is more than 200 times the temperature at the center of our sun. And that produces, as I say, the final product is helium. Now, what the video doesn't show is the final instability, which is that the magnetic fields produce high-frequency radiation called synchrotron radiation, which periodically in little bursts starts escaping. That drives down the magnetic field. And if people know Maxwell's equations, if you drive down the magnetic field very rapidly, you get an electric field. So this produces a tremendous electric field that accelerates an ion beam out one end and an electron beam out the other. So, as we'll show in a second, the ion beam carries most of the energy in a convenient form out of the plasmoid. So these plasmoids are not just hypothetical. We and dozens of other researchers have actually taken pictures of them. This is a picture, false color, this is a black and white picture of a plasmoid in our own device. So this is a rather large plasmoid, which this is 1 centimeter from here to here. So this is a few millimeters. We want them smaller because the smaller they are, the denser they are, the more fusion. So this is a picture of one of our densest plasmoids. This is 200 microns in radius. And this is a picture of the filaments that the animation showed. And you can see in this particular shot, the filaments are very well organized in this direction, but in the forward direction are starting to get disorganized. And we'll talk about that in a minute. So this is what you would call an animation of real observations. This is a film created by different shots taken under the same conditions, but with our fast ICCD camera recording the shot at different times. So it becomes the equivalent of a movie. And you can see that as the sheath moves down, the filaments form, but at the leading edge, they start getting disrupted. This is from experiments we did a couple of years ago. Now, all of this, you don't have to take my word for. We have published this in leading peer-reviewed journals. Our results are the best of any private fusion company, measured by the ratio of the fusion energy produced to the total input to the device. So in fusion energy, in the research stage, which all of us still are in, the goal is to get more energy out of the device than you put into it. Some of you may have read claims that net energy has been achieved by the National Ignition Facility, and that's not strictly true. They are getting more energy out of the pellet than the laser puts into the pellet. But the laser is very inefficient, and it takes 100 times more energy to run the laser than the fusion energy that they get out. So we're running with, our initial experiments have been with deuterium fuel, which is convenient to run with, and there's a lot of data. So even though we have the most fusion energy out per energy in with deuterium fuel of any private firm, that's still a factor of 100,000 less than net energy. Now, the main way we're going to get to net energy is by switching to a much more energetic fuel, which is hydrogen boron. Again, this is an illustration that our results, this is focus fusion, LPP fusion, is very close to the best results achieved by the giant JET project, which just ended. This was a multi-billion-dollar project of the European Union. And this is, again, running with deuterium fuel. The records that were achieved by NIF were running with deuterium tritium, which, again, is a much more energetic burning fuel. We don't use tritium because tritium would A, make our facility radioactive, and B, since it itself is radioactive, we won't be able to get a license to use it. So we use strictly non-radioactive fuels. And after 16 years in operation, our lab recently was inspected by the New Jersey Department of Environmental Protection, and they could detect no dangerous levels of radiation. So let me get into some of our recent progress. First of all, back in 2019, before the pandemic, we transitioned from tungsten electrodes to our final electrodes, beryllium. Beryllium was chosen because beryllium is extremely transparent to X-rays. So the X-rays are not going to be deposited in the electrodes, but can pass through them. And second of all, beryllium has only 4 charges, per nucleus. And the impact of impurities when the beryllium, tiny amounts of the beryllium get into the plasma is proportional to the square of the nuclear charge. So there's a huge difference between 4 squared, which is 16, and tungsten, which has 74 nuclear charges, squared is in the area of 5,000. So this is a big difference. And because tungsten has a very difficult to remove oxide layer, it actually erodes much worse than beryllium, where the oxide layer can be removed by simple hand polishing. So you can see this is one of these veins on the outside of the cathode, and you can see the difference between the cathode, the tungsten cathode, and the beryllium cathode after 200 shots. The beryllium cathode is pristine. This year, we are proud that we have achieved new records for deuterium fusion yield. So we've exceeded the records we first made back in 2016, and in all these years, no other private fusion company has gotten close to these records, so we're beating our own record. We've started to transition to running with hydrogen boron fuel, which is in the form of a compound called decaborane. So we've achieved the first pinches where the plasmoid forms, but we haven't achieved enough boron fusion to detect the reactions. It's a little difficult to detect these reactions because the alpha particles don't get out of the chamber. And we can't put alpha particle detectors in the chamber because there's too much energy inside the chamber. The instruments would not survive. So we have to rely on a secondary reaction where the alpha particles that are produced by the fusion reactions then have a second reaction with boron. In that second reaction, they produce a neutron we can detect. So basically, unfortunately, those neutrons, there would be something like 100 or 1,000 reactions for one neutron. So we haven't gotten enough neutrons out yet to positively detect hydrogen boron fusion. And we're starting to use mixes of deuterium with PB11, with decaborane fuel. This is because we know what the deuterium is doing. The deuterium tells us by producing the neutrons, and we can study the breakdown, which is the process of converting the neutral gas that we filled the chamber with to an ionized plasma. We can study that critical process more easily with the deuterium mix. Another thing that we've achieved in the past year is to get fewer and more powerful filaments. We calculated about 2 years ago that one of the problems in achieving high yield is getting the filaments strong enough, the individual filaments carrying enough current to contain the very hot ions. So we calculated that the 128 filaments that we were producing were dividing the current up into 2 small pieces. So we modified, we had a machine shop locally modify our cathode so it would produce 64 instead of 128. So we actually doubled the amount of current per filament. Experimentally, we got half as many filaments, and they were lasting longer. So instead of being totally disrupted, the filaments are still present at the front of the current sheet that's over here, and the filaments are still present. They're obviously not as regular as we want them to be. We want them to be very regular, to have extremely symmetrical compression, but they are there. Ignore those things. Those are on the ICCT chips. We have to clean those off. So this gives an idea of our recent progress. This is since we installed the modified beryllium electrodes. This is our third set of electrodes, or our third modification of the electrodes. And since we installed these electrodes back in September of last year, we've had a big rise in fusion yield. We've also found that we can clean off the anode from tiny particles that are produced from the shot by a cleaning mix of deuterium and nitrogen. And if we only count the shots that are made after the cleaning shots, then they look like that. So most of these low yield shots are the ones that we knew wouldn't produce high yield because they're the cleaning shots. This also, by the way, shows one thing about research. Research does not proceed in a straight line. You can see ups and downs, and that's not random variation. That's us deliberately changing the conditions to search for the way up. The way I relate this to people's experience is research is very much like a mountain hike. And if you've been on a mountain hike, you know that you can't climb a mountain by only going up. The trail always goes down. And even though that sounds like a waste of energy, it's the only way to get up the mountain is going ridge by ridge. And that's what we've been doing in a research program that has lasted quite a long time. We've been doing this for 16 years at our facility up in Middlesex. And like most research projects, it does take longer than you think. So you're seeing this for the first time among the general public. These are some pictures that we've taken over the last couple of weeks, which shows the problem of cleaning off the boron products. So we found that the boron actually chemically reacts with the beryllium to produce this pinkish substance, which is beryllium boride. But with our cleaning shots, as the cleaning shots proceed, we can see that it's being eroded. First, you have this phenomena of the erosion producing tiny grooves. These grooves, again, this is about 1 centimeter. These grooves are spaced about 100 microns across. This is a phenomenon we see even in water erosion. So over thousands of years, water will erode sandstone or some other very even, smooth material into these linear grooves. So that's what we're seeing here, except the erosion happens over a millionth of a second instead of 10,000 years. And we're seeing that this process is starting to work because these have the pink color, which is intrinsic to beryllium boride. But I don't know whether you can see this on the screen. Can people see that this is starting to become rainbow colors rather than pink? So that means we're getting to the stage that the layer is so thin, the colors are being produced by the interference of light, such as the colors of a soap bubble. So that shows that we're making progress. Now we want to redesign our cleaning shots so that we can do this in just one cleaning shot instead of a dozen, but we are making progress. And this shows how the cleaning is actually proceeding. So this is the top of the anode, and this is the bottom. And the top is being cleaned more thoroughly because the sheath proceeds downwards and accelerates. So this part is exposed to the radiation from the sheath for the entire 1.8 microseconds. This is exposed for less and less, and this, of course, is only exposed for the very end. So the cleaning is you can see the color up here is much grayer. And finally, this is sort of an indication of what we need to clean. This is the very top of the anode. This is the insulator. And you can see these little particles, which are presumably beryllium. Those are things that shouldn't be there and that we need to clean off, because if they're there during the shot, the current concentrates irregularly. And again, for good compression, you have to have a great deal of symmetry. An analogy is if you're trying to get 10 or 12 motorboats to converge within the smallest circle, they all have to be running at the exact same speed. If some are slower, then the size of the circle that they're in, the minimum size, is much greater. And that's what we find. If there's a little bit of asymmetry, you get much less density and therefore much less fusion, because the fusion rate goes as the square of the density. So the next steps are optimization of the breakdown, which means and of the cleaning. Then we're going to move from the mix to pure decaborane fuel. And finally, we're going to increase the power of our machine. Our machine actually has 12 capacitors on it, but only 8 are attached. We're experimenting first at the lower level. So sometime this year, we're going to attach the other 4, and that's going to boost our current from approximately 1.8 megamps to approximately 2.4 to 2.7. So since that's going to make our filaments bigger, everything's going to get better. Theoretically, there's a scaling of the current to the 8th power. So we expect a big boost in yield, and that's when we expect to enter the stage where we're trying to get net energy. So finally, I have a few more minutes. Yeah, I want to explain how we expect to get energy out of the machine. So after we complete the research phase and we get net energy, we need a much bigger engineering phase to create a lab, to transform a lab device into a working fusion generator, which can roll down an assembly line like a car. So these generators will be small enough that you're not going to be building them on site like a fission reactor. You're going to be manufacturing them like automobiles, which again will make them much cheaper. So this is how we expect to get the energy out. So there are 2 main methods. One is the beam of ions that comes in this animation and moves downward. So this is a pulse about 100 nanoseconds long. And when this pulse enters an energy collection device, which is simplified as this coil, it creates a magnetic field. So again, if you have a changing electric current, di dt in technical terms, you create a changing magnetic field. That changing magnetic field induces a changing electric field that is azimuthal. So when you have a coil or a more complicated geometric pattern of a conductor, you create electricity in the conductor. The conductor in turn creates a contrary electric field which slows down the beam. So you have a transfer of energy inductively from the beam to the current in the coil. So the current in the coil flows to a second set of very fast capacitors that will store the energy. Part of that stored energy will be used for the next pulse, and part of it will be fed to the grid to be converted to alternating current. Now, the trick here is, as this exits the coil, everything will happen in reverse. So what you need is a very fast switch which closes as soon as the charge has been transferred to the capacitors and doesn't allow the backflow. So that's another, there are such switches based on diamonds, but that's another challenge for the engineering part of the project. So, so a third of the energy is released in the form of X-rays. So the X-rays are captured in a device of our own invention. This is a patented device that's based on the extremely well understood photoelectric effect, discovered a century ago by Einstein. So what happens is the X-rays pass into a series of conducting plates and electrical grids. So for each of these thin conducting plates, some of the X-rays are converted through the photoelectric effect to electron energy. So the electrons exit these thin plates, and that's why they're so thin, so the X-rays, the electrons can get out of them without losing much energy. And they're captured by these charged grids. So the grids are charged at various voltages to capture the electrons at various energies. And we've calculated that this device can operate at about 80% total efficiency. So again, this pulse of energy is captured and fed into a fast capacitor, and from there into the grid. So the ultimate aim is a compact 5 megawatt generator which pulses 200 times a second. That's about as fast as a gasoline motor fires its spark plugs, with a capital cost with mass production of about 10 cents a watt, which is about a factor of 10 cheaper than any existing energy source, and with an electric energy cost of about half a cent per kilowatt hour. This is about 30 times less than what we're paying here in New Jersey. The key challenges for the engineering part is cooling the anode with compressed helium, the material questions of the beryllium-boron compounds. Can we actually use these compounds to shield the beryllium from erosion, and getting the electrodes?
Ivy or Ivy Karamitsis?
Yes. Should have turned this off. So either we, in order to get the maintenance down, we want the electrodes to last at least a month. It would take about a day to replace them. So that's about 500 million pulses. So the erosion is a problem, the heat is a problem, and the reactions with the different materials is a potential problem. And finally, we're going to be functioning at a much higher temperature than the experimental device. Because this is pulsing 200 times a second, the background gas is going to be at about 2000 C, comparable with conditions within a jet engine or a rocket engine. So that means we're going to have different chemical conditions and different breakdown conditions than we do in the experiment. So all of that will take a project that is probably at least 10 or 20 times bigger. We now have a staff of basically 3 or 4 people. We'll probably need a staff of about 150 to 200 scientists and engineers, and a budget of much larger, maybe 150 or $200 million. So we raised this money from the general public through crowdfunding, and currently we're raising $2.5 million. And if you're interested, you can get information from WeFunder, which is the crowdfunding platform. We're not allowed to discuss the finances outside of that platform. So thank you very much, and I hope we have time for some questions.
The fuel, your beryllium boron fuel.
No, there's a hydrogen boron.
Okay.
Right.
Okay. How much energy, what is the cost of actually producing the fuel for this?
Well, I'll give 2 answers. One is what's the cost now, and what's the cost at mass production. We know the cost of mass production is very low because, first of all, these are very abundant materials. If we convert the entire energy consumption of the world to hydrogen boron, we would have to increase the production of boron by 10%. So it hardly even matters to the boron industry. We know it's cheap to produce because early in the history of the space program, the United States government considered decaborane as a chemical fuel for rockets. And they produced tons of it. So we know it's pretty cheap to produce in mass production. Right now, it's quite expensive because there's no demand for what we need. We asked companies to produce isotopically pure decaborane, that is, with no B10. We wanted to avoid the B10 because if we get this to net energy, the B10 would produce, by a fusion reaction, beryllium-7. Beryllium-7 is radioactive with a half-life of 2 months. So that's too long to wait out, and it's so short that it's highly radioactive. So we didn't want any of that. So we got a Russian company and a Czech company to collaborate to produce 100 grams of isotopically pure decaborane for $600 per gram. But this was strictly because they were producing it by hand in a laboratory, not in a factory. Then Syed, my colleague, Dr. Syed Hassan, realized, why should we be using this precious fuel when we're doing experiments that aren't producing enough fusion for us to even detect? So he looked up the standard non-isotopically pure decaborane with 80% as much of the fuel, and it's 10 times cheaper. It's again produced just by laboratories, not mass production. So naturally, we're now using the $50 a gram version. And that's pretty good because even though $50 a gram sounds expensive, each shot is about 0.2 of a gram. So you're talking about $10 per shot. And our time is much more expensive than that. So even now, when we have no mass production, the fuel is not really a significant cost. And with mass production, it will be totally insignificant because remember, you get 1,000,000 times as much energy from a gram of decaborane as from a gram of gasoline. So
do you think it'll take for this methodology to be used for producing energy?
Right. Yeah, that's a tough question because if you look at the history of fusion, pretty much all fusion researchers, and I'm afraid I have to include myself, have been overly optimistic about time. So I thought that this project would take, 3 to 5 years for the research phase. It's taken triple that so far. So it's very difficult to estimate. One thing we've changed is estimating the number of shots it takes. That's much more accurate. And so far, we've put this on our website. So far, we're pretty much on track. We thought that it would take 800 shots to get from the first beryllium electrodes to 100 joules of boron. And I think we're still on track to achieve that. So let me basically say, if everything goes well, and if we get enough funding, which at the moment we're not, but if we get enough funding, we expect to get net energy within the next 18 months. And we expect that with this much larger amount of money, $150, $200 million, we could get a prototype generator working by the end of the decade. So if we get a prototype generator working by the end of the decade, since the amount of capital needed is far less than for existing energy sources, we think a transition to a fusion-based economy would take about 15 years. So before the middle of the century, we would basically get rid of oil and gas as an energy source. And then you.
Regarding boron, I went for muscle testing 10 years ago, and the practitioner said I had a deficiency of boron in my body. Is this the same boron, and how does it work specifically in your project?
Right. So chemically, boron is essential, is an essential nutrient for all life, both animals like ourselves and for plants. For plants, it's dangerous to have too much. And that's one reason that desalination plants have to be designed to take boron out of seawater. So if we ever run out in the far future of boron in the ground, we can go to seawater and we'd have approximately 3 billion years of energy at present rates of consumption. So this really is unlimited energy. So boron is necessary to us. Decaborane is a specific compound of boron and hydrogen. That's not good for us. It is somewhat toxic, but not very. And if you measure toxicity per unit energy, it's much, much less toxic than gasoline and oil. So we've had no problems dealing with it in our small lab. Yeah.
And the other question is
Yeah.
kind of not related to
Right.
that one. Zollner, I think is the author, says that there's a uranium mafia that's operating globally. Do you all have to deal with them?
Well, that's one of the, if you look at the social impact of having a focused fusion-based economy, one of the things you can do, we've had the military confrontation with Iran, you could put a lock on every uranium mine in the world, and there aren't that many of them. And uranium would simply go out of existence because really there isn't a lot of use for uranium. Not sure there is. Yeah, there isn't a lot of use for uranium other than the fission industry. And fission would become totally uneconomic. It would be very much more expensive than focused fusion. So that proliferation would be completely out of existence. And people ask, could this device be used for any military use? And basically my response is, well, obviously dual use is impossible to eliminate. If you can use this to drive a ship, you can use it to drive a warship. But as a weapon, while it weighs 3 tons, you could drop it on somebody's head. But there is no way, and I want to emphasize this because there have been a lot of movies, quite a few, that use the plot device of a fusion generator being converted into a hydrogen bomb. That was a plot device of a Batman movie. That is utterly and entirely physically impossible. This machine, if something goes wrong with it, it stops. Now that would be a problem for an energy production, but there is no way that this could be either converted into a bomb or could have a meltdown accident. The amount of energy in this machine at any given time is of the order of 100 kilojoules, which, as I say, is literally peanuts, or pistachios if you prefer them like I do. Yes?
Yeah, so from what you've said, it looks like money is one of the bottlenecks that you have to move forward. So my question is, if this technology is as promising as you have painted it to be, why would there be not lots of people wanting to invest in it?
Right. In other words, if you're so smart, why ain't you rich? Right. Okay. There's 2 big reasons for that. One reason is we decided long ago to set up our firm so that we do not sell voting shares. The only reason for this is to prevent a hostile takeover. It does not take a financial genius to realize that if we succeed, we will be worth far more dead than alive to the oil companies. The oil companies would pay any amount of money to suppress this technology. This is not hypothetical. When I was looking for work when I first left school, one of the first jobs offered to me in Washington was at a library of Chevron. And my job, as it was described when I was offered it, was to review the patents that would be relevant to the oil industry. And I said, oh, I get it, so that we would start winnowing down the ones that would be interesting for Chevron to develop. And he said, no, not generally. Generally, we're interested in the ones that we want to buy to suppress them. Because remember, this is totally illegal. It's not illegal to suppress technology, to slow technology down, to increase profit. That's the way capitalism operates. But in this case, we have to avoid that at all costs. Not being able to buy voting shares means that 99.9% of VCs, venture capitalists, will not touch us. So that leaves out that. Not being able to control pretty much eliminates billionaires as well. In the early stage of the project, I probably talked to 22 dozen people, all of which had high enough net wealth to write me a check for the entire project. And the amount of money we got from them wouldn't have gotten me on the subway, because they all wanted to control. They wanted their own toy. We see this in the fusion industry. Peter Thiel has Helion. Paul Allen, who's now passed away, was one of the initial investors in TAE. We don't have a billionaire because so far we haven't had one that doesn't demand control. And then there's a secondary issue, which is them that have gets. If you look at the coverage of the fusion industry in the mass media, it is very explicitly covering those that have the most investment, not those who have the best results. And if you just look at the rankings, they're ranked by total investment. So we're not going to be in the top 10 by total investment. When science journalists say, hey, this is an exciting story, you know, company in the garage doing better, we're actually in a storage facility, doing better than multi-billion dollars, that's a great story. It's killed by the editors. The editors say this is a business story. Fusion is being covered as a business story, not a science story. So because we don't have mass media coverage, people ask the same question. Well, if you're doing so good, why don't I read about it in the Times? We are working on solving these problems. For one thing, we think eventually our results will get published in such a way that people can't ignore them. We are reaching out to various people who do have high net value. Crowdfunding can finance us if we reach enough people. So we're fine-tuning the way to reach a bigger audience. But the key issue of maintaining control is probably the biggest issue we have, and we really can't change that.
We'll have to stop the questions right there, but I'd like to invite our other speakers, our lead up to join us. And Rob, you too, and Bob Wilson, would you come up? I have something for each of you.
Okay.
So, 2 items. The first is a
Oh, a
Big
medal.
Bang Mile and Science Festival medal.
Oh, wow.
Oh, made out of real metal, not even plastic. That's very nice. Thank you.
You don't have to run a mile for this. And I have T-shirts as
Oh,
well.
wow.
And so, let's see, maybe a medium, and I've got a couple of larges. Large.
Yeah.
Okay, and
So you see, we all won first place.
so once again, we'll need to vacate the room by noon. If you would, please clean up. There should be trash cans. See the black screen there? There's places to put trash there. And thanks again for coming, everyone.
Thank you.